Hello ladies and gentlemen, and welcome to Student Misconceptions in Chemical Bonding, Origins, Diagnosis, and Treatment. This is my presentation for Dr. Fellner's Research Methodologies course at Lehman College. I'm going to begin by talking about the importance of misconceptions. Now, it has been identified that all students enter the classroom with knowledge that they gain from many different realms: their personal experience, their previous classwork, their parents, the culture in which they're surrounded, and it's well known that this knowledge mediates student learning. It's really through all of the conceptions that they've already built that students gain new knowledge or build new knowledge. And effective teaching, pardon the spelling there, requires that teachers sort of allow students to grow within their zone of proximal development. And in order for a teacher to do this, the teacher must be aware of students' prior knowledge. If they're not, and they don't know sort of what conceptions and misconceptions students begin with, and it can be incredibly difficult to change those misconceptions without any sort of awareness of them. So where do the misconceptions begin? Like I said, personal experience is already the number one source of these misconceptions, but in a course like chemistry, where many concepts are abstract, they're things that cannot be seen ever, like bonds, students might not actually have any conception at all. No misconception, no scientifically accurate conception, simply no conception. And when they develop misconceptions, it is generally found that these are the result of misleading sentences, which are found in many, many high school textbooks, as well as models that are used to try and make abstract ideas in chemistry visual. The problem being that these models are misleading, and students take them to be accurate representations of the world or of the concept at hand, and they take those models in and later on will express ideas that suggest they do not actually understand the way that atoms bond together. In order to diagnose misconceptions, one has to first find out what students are thinking. And there are always different options. I've broken them up into two categories here. A teacher can do an interview with the student or pen and paper, and perhaps the pen and paper is still an interview, because you can offer open-ended pen and paper questions. Or there are multiple choice diagnoses. And when you go through the literature, most of the diagnostics for misconceptions in chemical bonding are done with multiple choice questions. This being justified because they are certainly the easiest to grade, they're the fastest to grade, and they allow for a large sampling of students to be diagnosed very quickly. Interviews are a lot more time consuming. They require coding, they require perhaps a little bit more in-depth analysis, and for this reason they're generally eschewed in the literature. So I'm going to give you a chance to take a look at 3 questions from Tan and Trigast's diagnostic assessment for misconceptions in chemical bonding. I'm going to show you the question and the answer choices and give you a moment to choose your answer. You might pause the video at that time. Once you've chosen your answer, you can go to the next slide, or we will go to the next slide, I should say, where you will find the results of a chemistry class, high school students in the South Bronx. Their results on these questions, I will have circled the correct answer, and I hope you're excited to get started. The first question. Now, when my students answered this question, these are the results that we have. I did a chi-squared test to check the statistical significance of these data, and in fact, for this question, the data were significant. Now, you should notice 2C, the correct answer. I had 2 students choose that, which is approximately what one would expect to account for with student guessing. Question number 2. The results of this question, or the data I should say, are quite different from the results of question 1 and question 3. As you can see, there is a heavy leaning towards answer 2D, which is in fact the correct answer. And a chi-squared analysis suggests that these data are very, very, very much so significant and cannot be the result of pure chance. And finally, question number 3. Now, a quick glance at the chi-squared data here suggests that these numbers are in fact not statistically significant, although more students did answer 1A than any other question. That can be explained by simple guessing and probability, and I will get into the analysis in a moment. So an initial analysis. In the first question where the data were significant, there were 2 answer choices that prevailed. Both of them were wrong. The very first one falls in line with a previously identified common misconception. That is, a misconception that in the literature up until this point has been stated to exist frequently in the student population. That is, more than 10% of students in chemistry have this misconception. The other answer that prevailed is nonsensical, suggesting that students do not know anything about this topic, or perhaps not enough to make an informed decision. So an analysis of this from Tan and Trigust would suggest that approximately 1/3 of my students possess the misconception that atoms share electrons in a salt, when the reality is that after 1 electron or more is transferred from the metal to the nonmetal, the atoms are actually held together by the electrostatic force. That is, positively charged cations are attracted to negatively charged anions, and one can imagine them almost as positive and negative spheres sitting next to each other. There's certainly no sharing of electrons taking place. Now, I do have a doubt about this misconception actually existing, because this diagnostic was given before the unit began as an attempt to diagnose any misconceptions that already existed in students. And the fact is that this is a misconception that is always explained in the literature as being the result of using ball and stick models to teach students about lattice structures, about how ionic compounds are held together. I was aware of this origin of the misconceptions, and for this reason I never used these models, so I was skeptical when I saw these data. The second question, initial analysis. The correct answer choice prevailed. 70% of my students understand that boiling points and melting points are related not to intramolecular forces, that is, covalent bonds between, say, hydrogen and oxygen atoms and water molecules, but instead to the intermolecular forces holding the different molecules together. And question number 3. There is no statistically significant difference between the answer choices. The chi-squared was 0.2. So on this question, this is what we would have expected for every question, because this was given prior to any education about the subject. Students were guessing, and we cannot assume that they have any conceptions, correct or otherwise. After giving this diagnostic, I then chose 4 students at random for a loosely structured interview. The plan was to talk to them about the answers they gave, ask them what they chose, why they chose it, just to get sort of a closer look at student thinking. I began the interview by asking students how it went, and they all quickly announced that they had no idea what any of what they read just meant, and that they were guessing. Now, on closer analysis, it turns out that they did have some clues, but on the whole, they really were not familiar with the vocabulary that these diagnostics included, and for that reason, they had to make some educated guesses. So, upon further interview, it was clear from the first question that students did not understand the lattice structure of salts. They were not thinking about salts in terms of molecules at all, in fact. There were two students, who were not even aware that sodium chloride was a salt. So for that reason, they were not able to engage the question the way that its authors had intended. And the other students, while they did in fact choose the correct answer, were not able to explain it when we were speaking. They said, "I remember you saying salts are not molecules." So I'm going to ask them why. They could not explain. And the second question, which most students got correct, talking with them became clear that they did not understand the difference between intermolecular forces and intramolecular forces. And in fact, some of the students showed that they actually believed that when a substance boils, that the bonds that hold the molecules together are broken. Not that the molecules become spaced far apart, the molecules themselves actually break. This is a huge misconception that this diagnostic was not able to diagnose, in large part because in question number 2, 3 of the answer choices included vocabulary words that a student who has not been in a chemistry class probably will not be familiar with. Those words are macromolecule and perhaps molecule. In question number 3, perhaps the most interesting thing is that while the results of the student answers suggest that students were guessing, there's one student who also chose the wrong answer, but who was able to fully explain correctly the problem itself. And when speaking with other students, it became clear that they were still grappling with this idea, with sort of the more basic ideas. That this diagnostic seems to be designed for higher level students, and what my students were dealing with was simply understanding basics of the energetics behind bonding, and they had developed some misconceptions within that. These are not misconceptions that the literature identifies as common, but there were certainly misconceptions in my classroom, and they needed to be addressed in order for students to move on with the curriculum. Now, the conclusions that I've made from my own research and grappling with this literature. The Tannen-Triest diagnostic, it turns out, is not the only multiple choice diagnostic out there for misconceptions in chemical bonding, but I think the problem that we're always going to face with these multiple choice diagnostics is that prior to the administration of a new unit, they're really not sufficient for diagnosing student misconceptions. The problem is that these diagnostics are designed to uncover common misconceptions. That is, they have answer choices that lead students down the path to showing their own misconception, which has been found to exist at a high level amongst the general student population. The problem is that misconceptions have existed in populations across a large portion of the population. A great example of this being the idea, for instance, that when one came down with the mumps, that this was the result of a mumpish evil spirit inhabiting the body. Now, I believe that today most students would find that ridiculous, and they would suspect that this were a bacteria or a virus. But if that answer choice were on the diagnostic, then students might reveal, quote unquote, that they have this belief that mumpish evil spirits inhabit humans with the mumps, when in fact they do not have that idea at all. And in order to diagnose misconceptions that students have prior to a unit in which they're going to learn new vocabulary and they're going to need to be fluent in that vocabulary, interviews, although time-consuming in their administration as well as their analysis, they are far more effective. In my conversations with students, I was able to unveil large misconceptions that were incredibly useful to know that my students had, and then explicitly addressing them in class actually reduced a lot of them in the long term. And I think that going forward, a great focus for research would be actually developing these oral diagnostics to help educators have these questions that they can ask of their students and diagnose their misconceptions orally. Now, once the misconceptions have been diagnosed, then it becomes time to treat them. And as Osmond points out in his article, it's the educator's job to learn about what the common misconceptions are and how they arise so that those might be either prevented or treated. Now, I just wanted to give an example